All right, so last time we started our discussion of rational numbers, and we're going to continue this section today, finish it up. There's a few more features of this section in particular that we're going to talk about, and 6.5 is a denseness property. So if you have two fractions, then what the denseness property says is that there's some other number, rational number, between them. And anytime I think about this, I think about the movie IQ. Does anybody know that movie? It's just you and me. All right. Well, in the movie, it's Meg Ryan's in the movie, and no. The movie, well, now that nobody knows the movie.
I've seen it.
Meg Ryan is the daughter, niece, I think it's niece of Einstein in the movie. And I think it's Tim Robbins is her opposing character or whatever. Anyway, there's a point where she's very, very intelligent, right, niece of Einstein, yeah. And she says something about the fact that you can't ever actually meet at a point, because in order to do so, every time you do this, you have to half the distance. And if you always half the distance, you'll never get there. Well, that's related to this idea of denseness property. The idea that being that anytime you've got two numbers, you can find a number between them because all you have to do is half the distance. And you can continue that process, so there's lots of numbers between them. There's not even just one. There's plenty of them. And so this theorem, Theorem 6.6, actually tells you a way to do that. Now, some fractions, it's easy to look and say, oh, I know what the fraction is between it, because either it's values you're familiar with, or because it's very easy to look at. For instance, if you had, let me do 5/10, I know I'm writing them improper, or not simplified for a moment, but just bear with me, and 7/10. Then you don't need Theorem 6.6. You can tell me a fraction between them. It's easy, right? What? 6/10. I mean, so we don't need this all the time. But what if instead of giving you 5/10 and 7/10, I gave you 5/10 and 6/10? Well, technically 5.5 over 10 would work, but that wouldn't be in rational number form. Yeah. And you know how you can get that easier? Well, yes, but you can use this theorem, and this theorem does exactly that. What this theorem does is this theorem says, and it wouldn't even matter if the denominators matched or not. Okay, I was checking something. So in this theorem, what it says is that in order to find, you've got two fractions, and you want a number between them, you can actually add the numerators together, and it becomes the numerator. You can add the denominators together, that becomes the denominator, and that new fraction will be between the first one and the last one we looked at, which is pretty handy. Okay, so we're going to use that fact, and we're going to take a look at the rational numbers, 33 over 427 and 34 over 427. And despite the fact that Brendan was doing great math in his head, because he can, and he's done this for me before, those numbers are kind of awkward, aren't they? They just aren't really nice numbers to work with. So having this theorem back on the previous page is actually really helpful because it tells us exactly how we can find a number between them. So what am I going to do?
Add 33 and 34.
And I'm going to write them over what?
427 plus 427.
Right. Okay, so it's 33 plus 34.
67.
And what is 427 plus 427?
64.
Occasionally you'll come up with something that's able to be reduced, but most often you actually will not. Okay, so any questions on that one? So you can do this all the time. You can always do this. You can even do it with the numbers, like if you really felt so inclined with the 5/10 and the 7/10, it would still work. You could still do it. It wouldn't hurt anything. Okay? All right. Question that you should be aware of and you should be able to answer is, why must this always happen? Why is it that there always is a number between them? I mean, like I told you can half the distance. Why?
You can always get closer. It's like infinity.
Yeah, well, sort of. It's not an infinity. Infinity means you go forever out, right? This is the idea that there's an infinity kind of number. There's an infinite number of numbers between two numbers. It's called denseness. So the idea is that it's actually on a continuum, right? It's not like we just take steps from one number to another and we kind of bounce along. There's actually space between here that we can move. Does that make sense? So the issue is that, or one way to think of it, let me write it this way. Is as a number line. So if I've got these particular points on the number line, I'll use the ones that are just in the problem above. So in our minds, they are very similar numbers. They're nearly the same value. If you put them in your calculator and look at a decimal for them, they're awfully close in decimal form. But the reality is that they are somewhere along the number line. And I'm sort of zoomed in. So imagine your graphing calculators that many of you have seen and we used and worked with before. And when you keep zooming in, all it does is sort of spread things apart, right, when you zoom that in. Well, same thing here. Eventually, you see that there's this gap between them. It didn't look big to begin with, but now it's big because I zoomed in. And so this gap between them, every spot in that gap corresponds to some number. So all of these spots and plenty others actually are numbers between the two. So one way to think of this is a number line. I'll fix that. Thank you. All right, every location on the line corresponds to a number. So there is space between any two, or there is a number. I'm going to run out of space, but a number in the space. We'll say it that way. There's a number in that space. And all we're asked to find typically is one. But if we were asked to find another one, could we? What if I were asked to find two numbers between 33 over 427 and 34 over 427? I found one. Now what? Okay, so picture what you're doing here. The imagery is this. This point right here, I don't know that it's exactly that point, but that point right there is what we just found to be 67 over 864. How do I find another one of those red hash marks?
Are you going to add that with one of the others?
Yeah. So we're going to find a number between by using one of the original end numbers that we had and the number that we found that I just marked in blue. And so we can find, we could keep this process going. We can find as many numbers as we want between them because there are an infinite number between them. Does that make sense? So we could sort of just repeat this process. All right. This is actually a fairly common mistake. A student simplified the fraction m plus n over p plus n to m over p. How would you help the student? First of all, it's an error. So if you already looked at that and said, well, I don't know what's wrong. So what were they doing? There's a couple things. Okay, so they crossed out like this. Well, but n is equal to n. So why can't I do that?
Because there still can be different numbers.
But n can't be a different number. N represents the same number on top and bottom.
Because they just completely, it's like they canceled out. They didn't.
Okay, so let me pause for a second and ask you a question. Oh, okay, there we go. So sometimes we can do this. Do you agree? Sometimes we can do this sort of a marking through something and it just eliminates. But we do that when, Mackenzie?
When you multiply.
When you're doing multiplication. Okay, that's a multiplication feature. In fact, we saw it earlier on in this exact lesson, reducing fractions, right? To reduce fractions, we can either multiply the top and the bottom or divide the top and the bottom by the same number. But that's a multiplication feature. That's not an addition feature. So what might you say to the student now that you sort of understand what they've done? Okay, so you're going to explain the rule.
The multiplying.
Okay, so one thing you might do is tell them that if it's multiplication, they're correct. All right, it's a good thing to do is to tell the students what they did right. So if you were doing multiplication, that would work. Okay, so that's a good thing to do. So one thing we might say is that, let me do it this way. If you were multiplying, this works. And you could give an example of one where it works, right? So you could do something like, if I had 2 times 5, over 2 times 6, that would be the same as 5 over 6. All right, I could just sort of do this line through the 2's. So how am I going to explain to them? Because while I can definitely say it's a rule, it doesn't work. Some of your kids aren't going to like that very much. That doesn't sound very helpful. Right? It's like when I tell my kids, I'm the mom, that's why. They don't like that. And so basically when you're saying this is a rule, you're saying, I'm the teacher, that's why. Okay? So let's come up with something else. What else could we say to them? How could we show them that it's not going to work? Give them an example. Giving them an example is a really good way to do that. Okay? Show them one that doesn't work. So, and in fact, most of your numbers that you're going to pick are not going to work. 0 would work, right? I mean, like if you actually had the zeros there, that would work. So don't pick 0. So we can show them one that won't work. So give me an example. What could I let all my numbers be? I need numbers for M and P and N. I need 3 numbers, basically. Just pick some.
2, 5, and 6.
Thank you. All right, so we're going to do 2 and 5, and we're going to add 6. Okay? So let's do it by actually adding and see what we get. So what is 2 plus 6? 8. And 5 plus 6? 11. All right, now let's do what they would like to do, that is cancel out my 6's, and what do I end up with? 2/5. And the question is, are these equal? The answer is no. There's lots of ways you could show that they're not equal. In fact, we looked at some of those last time. We could look at that cross multiplication. But one really quick way, which sort of harkens back to, I don't remember which one of you guys mentioned it last time, is to notice that 2 over 5 is less than a half, isn't it? And 8 over 11, bigger than a half. So these can't work just intuitively by looking at the size of the fractions. So yeah, these aren't equal. And if they aren't equal, then this idea of being able to cancel out the n when it's plus n isn't going to work. Okay? And that's better than because I'm the teacher, isn't it? It is. I mean, it gives them a real reason as to why it doesn't work. Okay. We have one more in this section, example 8. I think that's right, yeah. All right, this says, if we take a set of numbers equivalent to 1/3 and graph them as points on the xy axis, so that the numerator becomes the x coordinate and the denominator becomes the y coordinate, what type of a graph would we get? So there's a lot going on in the question. Let's piecemeal through it. The first part says we want a set of numbers equivalent to 1/3. So we learned last week how to get equivalent fractions. We didn't learn it. We reminded ourselves. What's another fraction that's equivalent to 1 over 3? 2/6. 3/9. And I'm going to throw in one more that's going to be helpful for us to get the whole picture of the graph. -1 over -3. Because that's still 1/3, right? The negatives actually would cancel, kind of like the student wanted to cancel my ends earlier. Next thing it says, so this is the numbers equivalent to 1/3. It says graph them as points on an xy axis, so the numerator becomes the x coordinate and the denominator becomes the y coordinate. All right, so all of those numerators are now my x's, and I'm just going to keep them in the exact order from left to right that I have them. So 1, 2, 3, and -1. And then my y coordinates are the denominators, so 3, 6, 9, and -3. Does that make sense so far? That's what they asked. And then it wants us to graph them and kind of to describe what kind of a graph I get. Okay? So I'm going to graph. I'm going to try to do as accurate as possible up here, and you're going to do the same, of course. All right, so we've got some kind of a grid like this, and I need to put ordered pairs. So some reminders, this is my x-axis and this is my y-axis, right? The x-coordinate of 1, oh, and let me say this is the positive side and negative, positive and negative. So x equals 1 means moving to the right 1, and y equals 3 means moving up 3. So my location looks something like this. Move it off. The next one was 2, 6. So I'm over at 2 and up at 6. Something there. Have 3, 9. Which is fairly high up. And then I have -1, -3 down here. So if I were to connect those, what would the graph look like? It looks like a line. It is a line with certain characteristics as well. Can you tell me maybe what you're seeing?
Slope of 3.
Ah, so this is it says what kind of graph do we get? We get a line with slope 3, right? Slope describes how far up and over, rise over run you go, how steep something is. But there's one difference than what we've written down that we should probably identify. What is the coordinate of that point? 0, 0. Does it work? It does. 0 over 0 equals 1 over 3. No, it actually doesn't fit the pattern, right? All of the other numbers on the line, if I take the x-coordinate and I divide it by the y-coordinate, right? 1 divided by 3, I get 1/3. But this point, while it is on that line, does not have that feature. Do you see that? So this one actually does not fit the pattern. So this is actually going to be a line with slope 3. I'll write it down the way it actually really is. And a hole at the origin. There's actually a hole in this graph. There is a point that is excluded from this description. And jot yourself down the reason why. It's because 0 over 0 is not 1/3. And that's how all the other points are determined. Okay. Any questions on that one?